Hello everyone and welcome to our video. Today we're going to just recap work energy theorem quickly before moving on to the next section, which is conservative and non-conservative forces. Alright, this is one of the last few sections of this topic. Okay, so we're almost finished. Alright, now work energy theorem, just to recap, alright, is the net work done on an object. Alright, and that is the net work done on an object is equal to the change in the object's kinetic energy. Alright, so that was what we did in the previous video. We had a look at the example here, which we did. Okay, now we're going to move on to explain the conservation of energy. Alright, now the conservation of energy, we're going to be looking at the conservation of energy when non-conservative forces are present. Okay, now we first need to have a look at what is conservative forces and what are non-conservative forces. Okay, so a conservative force is conservative if the net work done by the force is 0 while moving an object around a closed path, starting and ending at the same point. Alright, so let's just go through that again. A conservative force is when the net work done by the force is 0, okay, while moving an object around a closed path. So this is very similar to the conservation of momentum, etc., etc. Okay, so a closed path, a closed system. Okay, and a closed path starts and ends at the same point. All right, just a quick thing to note is when conservative forces are present, total mechanical energy is conserved. Okay, now to explain the conservative forces a little bit better, we're going to have a look at an example. So let's take, for example, a 1 kilogram ball which is thrown vertically upwards, reaching a maximum height of 2 meters. Okay, now if you want to get a better picture of that, so here's a ball. Alright, let's color it in. So ball, okay, that has been thrown upwards, alright, 2 meters. The ball is 1 kilogram, okay, and it's been thrown vertically upwards, alright, by 2 meters, and that's its maximum height. So over here, where the ball is, this is its maximum height over here. Alright, there we go, 2 meters. The only force is the gravitational force, Fg, acting during the motion, alright, because it's free falling. You've thrown it up, and it's coming back down. Alright. So the path that is traveled is closed, alright? It's not going anywhere else. We're not playing pinball over here. We're just throwing a ball vertically upwards. Okay? Now we need to calculate the work done upwards. Alright, so W up, or the work done by up, we denote it by W up. Alright? So let's just let's maybe write it a bit better here. So the work done by up, that's how we'd write it. We know that's equal to F delta X, alright, cos theta. Okay, now we know that, right, the only force acting on the ball right now is the gravitational force. Okay, so we denote F there as Fg. We know what Fg is equal to is mg, alright, delta X, alright, cos of theta. Brilliant. Okay, and then we'd sub in there. Alright, it was 1 kilogram multiplied by 9,8 multiplied by 2 cos of 0, because the force is in exactly the same direction as the motion. Okay, and we get a, oh sorry, I was reading the next line, sorry, it's 1 times 9.8 times 2 times cos 180. Alright, because gravitational force is downwards and the ball was thrown upwards. Okay, so up until it reaches its maximum height of 2 meters, okay, it creates a 180-degree angle. Alright, and that gives us an answer of negative 19,6 joules. Now, the work done by the downward motion is exactly the same, gives us the exact same answer as above, except that it's positive because delta x now is in the same direction as the motion, or as the force. Alright, force and delta x are in the same direction as the motion of the ball, and that gives us an answer of positive 19.6 joules. So therefore, when we calculate the net work done on the object, negative 19.6 plus positive 19.6 gives us 0 joules. And therefore, the gravitational force is conservative. Alright? So we know that that is a conservative force, and henceforth, gravitational force is a conservative force in this example. Okay, that example seems kind of straightforward. Let's have a look at what is a non-conservative force. Alright, let's consider a ball rolled 5 meters up a rough slope that then rolls back to its starting point. Okay, let's have a look at how this example goes. So, all throughout the motion of the ball, a frictional force, let's say 30 newtons, acts on the ball. Right, so now the friction is always in the opposite direction to the motion. Work done by friction, in other words upwards because the ball was rolled upwards, okay, is F with the force of friction, delta x cos theta. Alright, we sub in our values. We know the 30 newtons times 5, cos 180, negative 150 joules. The work done by friction downwards, okay, is 30 times 5, cos 180, and that gives us 150 joules. Now, the reason why the work done by down is positive is because friction. Oh, the reason why work done by down is positive because friction is in the negative direction. All right, it should be. Oh, I made a mistake there. That's supposed to be. Oh, my bad. Okay, so I thought that this was a dash. It's actually not a dash. It's the same answer. It's actually negative 150 joules. What was I thinking? Oh my goodness. You see how important it is to write your work out neatly so that you do not get confused by your own work. Okay, sorry about that, everyone. Okay, so it's the same answer. So the work done by the upward motion and the work done by the downward motion is the same. It's still negative 150 joules. So if we add the overall work of the ball on the rough slope, it is 100. It's negative 150 plus negative 150. We get negative 300 joules, and therefore the net work is not equal to 0, and thus friction is a non-conservative force. And this will result in total mechanical energy not being conserved. Okay, now we also must note that the net work done by friction is path dependent, because if the ball was made to move further, more than 5 meters, there would be a greater net negative work done. Okay, so the path is dependent. Okay, net work is dependent on the path. Okay, alright, it's dependent on the path. Also, just one thing that we must note, applied forces are also non-conservative because they increase the total EM, or mechanical energy, due to positive work. Okay, so we know, what have we learned so far out of these notes? This is what we've learned so far. Okay, let's just get a clean board here. That we know that the gravitational force is a conservative force. Alright, we also know that the applied force as well as the frictional force, so force of friction, alright, we know those are non-conservative. Okay, and the way we denote non-conservative is NC. Okay, wonderful. Right. So let's calculate the work done by a non-conservative force. Okay, so let's suppose a trolley rolls down a slope from point A to point B. Okay, the trolley is rolling down from here to there. Okay. Now, if friction acts on the trolley, negative work will be done by the non-conservative force. All right. The work done by the non-conservative force, W and C, results from the force of friction. All right. So some of the mechanical energy will be lost due to this non-conservative force. But according to the law of the conservation of energy, energy cannot be destroyed. So the work done by the non-conservative force must be included. And the way we calculate the work done by a non-conservative force is the change in its kinetic force, or the kinetic energy, plus the change in the potential energy. Okay? So we know that the ball had to start from a height, right? Because here was our slope, or the trolley, sorry. There was the trolley. We're using just a circle to demonstrate the trolley. And here's point B. All right, we can clearly see here that there was a height involved here. Right? There was a height involved here, right? All right, let's just... Oops. All right. Not going to make that straight now. Okay, there's a height involved here. Okay, so over here, there was EP. When the ball rolls down here, okay, there's EK at the top. All right, so the work done by a non-conservative force is equal to the change in the object's kinetic energy plus the change in the object's potential energy. Okay, and that is the formula for how to calculate the work done by a non-conservative force. Okay, so what we're going to do now, all right, is in our next video we're going to have a look at an example at how do we actually use this formula, all right, when approaching a question. All right, so stay tuned for the next episode on work done by non-conservative force.